All right, we're back. We're on page 6 of notes 15 of Calc AB. What we're doing is we have a definite integral, and we're going to write a Riemann sum, and then we're going to take the limit of the Riemann sum. We're going to use all those formulas that we know, and kind of go from there. So let's see if we can do it. So these are like pretty straightforward once you kind of like get the idea behind it. So we need a delta x. So delta x is going to be, so you're going from 1 to 5, which means the distance between them is 5 minus 1. So 5 minus 1. And then we're going to make n rectangles. So divide by n. So we get even delta x, which is the base of each rectangle. So 4 over n. We need an x sub I. So x sub I is going to be where you start. So that's at 1. And then for each rectangle, you just add the base, which is delta x, that number of times. So if you want the evaluation point for the 10th rectangle, let's say, you're going to do 1 plus 10 times delta x. If you want the evaluation point for the 75th rectangle, you're going to do 1 plus 75 times delta x. So in general, you're just doing 1 plus I times delta x, which is 1 plus 4i over n. And then f of x is going to be this thing, which is, what happens when I highlight in black? It's not terrible, it's not great. So f of x is 3x plus 2. So let's write our thing. So as a function of n, the area, so this would be an approximation of the area, not like the actual area, is going to be equal to, from 1 to n, it's f of x sub I. Should I write that? I don't really want to. So I'm just going to do it. So it's 3 x sub I is 1 plus 4i over n plus 2. And then we need to multiply all of that by delta x, which is 4 over n, like so. Okay, so what we've done is we've done base times height, basically. The height, so I'm just highlighting x sub I here so that you can more easily see f of x. It's 3 times x sub I plus 2, 3x plus 2. And I do that all the time. When I'm looking at a Riemann sum, I try to figure out what the function is by identifying what I think x sub I is, and then I treat it as like a unit in my head. 3x plus 2, that's our function. Delta x is 4 over n. And so I think we're good to go. So here we go. I'm going to expand this. Equals 1. So I get 3 and then plus 2. Also, I'm just right off the bat, I'm going to pull this out. So let me get, I don't have my good colors with me. So I'm taking out 4 over n. Because it's just in the way, it's constant multiple. It doesn't depend on I. Anything that doesn't depend on I, you can actually factor out, provided it's a constant multiple. So here, now I'm going to get 3 and 2 is 5, and then 12i over n. So that's just distributing and collecting. So you have your choices here. You can rewrite this as 2 separate summations because the summation distributes over addition. Or you can kind of like go for it. I'm going to kind of go for it here. So I'm going to do 4, well, all right, I'll show more work. 4n times 5. And then it's the sum of 1, so it's n. And then plus 4 over n, 12 over n. And then the sum of I is n times n plus 1 over 2. So this is pretty good, right? And now what we need to do to find the actual value of the definite integral is we need to take the limit as n approaches infinity of this. So the actual value, the integral from 1 to 5 of 3x plus 2 dx, which if we wanted to do it, that's a trapezoid. Like we could do it. So maybe I'll do that in a second. And then I was going to check on the calculator to just see if we got this thing correct. This. So maybe, I mean, I usually highlight these. So like this is where this is coming from. And then this is where this is coming from, just in case. All right, so what do I want to do here? I'm going to make it 20n over n plus 40, I guess 48. I mean, I'm not really, well, it's fine. It's fine, just do it right. And then 2n squared. It's actually like a pretty easy, pretty straightforward limit to evaluate, right? This is just 20, and this is 48 over 2. So 20 plus 48 over 20 plus 24 is 44. Okay, so I was saying, this is just a trapezoid. And I know it's a trapezoid because you have like your x-axis. Let's say this is 1 and that this is 5. And then you take 1 and you plug it in here and you get 5. So you have one base. Okay, I don't know what that even was. I tried to like go back and forth on a line, and then the auto shape, I guess, just goes from where you started to where you stopped, potentially. Okay, so what am I doing? Plugging in 1, 5, and then I'm going to plug in 5, and I get 15, so 17. So accurate? No, but correct. So then the area of this will be 1/2. The height is 4, I should say, and then the sum of the base is 22. So that's 2 times 22, 44, which is what we got. That's what you want to be able to do. You want to just kind of like, just knock them out, you know? Like, so let's do this one. So delta x, you start at 0, end at 3, so they're 3 minus 0 apart, and 3 over n. X sub I, you start at 0 and you add I times delta x, so so it's 3i over n, and then f of x is your function, and your function is just x minus 2. So we can write the area as a function of n. So the area as a function of n is kind of like useful. It's an area approximation as a function of n. And then like you'll be given a number, like use 50 rectangles, so n is 50, and you just like plug it in. Like up here, if I had wanted to approximate it using, I don't know, 25 rectangles, I would have done a of 25. And you just jump down here and plug in 25 everywhere you see an n. It's like straightforward because it gives you a function. So this is pretty useful even without taking the limit, because you don't want to have to recalculate it every single time. So what are we doing? From 1 to n, here we go. So it's x sub I, which is weird. It's just 3i over n, and then minus 2. Okay, so that's f of x sub I, and then delta x is 3 over n. And then I sort of technically need another set of parentheses, but like, I don't, do I have too many parentheses here? Well, like, can you ever have too many parentheses? I think I have double parentheses that are unnecessary. I think these are unnecessary. Those are definitely unnecessary. I'll move this over just a tiny bit. All right, that looks okay-ish. So this one could potentially be harder if you're looking at it trying to like work out like what's going on. Like I see this is my x of I, so f of x is just x minus 2. It's almost like the simpler the function, the kind of harder it is to identify it. So 3 over n, I'm factoring out, equals 1 to n. Well, weird, because there's really like not much going on. So we have 9 over n squared, because I took out 3 over n. I have 3 over n already, and I took out 3 over n. And then the sum of I is n plus 1 over 2. And then there's a 3 over n, I'm taking out negative 2, so negative 6 over n. And then it's the sum of 1, which is just n. So this, I don't know, 9n plus 1 over 2n squared minus 6. Okay, so what do we do from there? This is our area as a function. It's an area approximation as a function of n. So if n is 5, plug in 5. It'll give you the approximation using 5 rectangles. I want to get the exact value, so I need to take the limit as n approaches infinity of this is this, the exact value of that. So I'm going to write that down, sort of. So the integral from 0 to 3 of x minus 2 dx is the limit as n approaches infinity of this thing. So I'm going to copy it. I mean, I recommend, I've come a long way on this, like, should we write on iPads type of, like, if that's an argument. 100% pro iPad now. I think everyone should do it. It affords you so many options. it's an expensive option though. Like, although I will say I have a Surface tablet also, just as good. But it's like kind of it's an expensive option. So, you know, your mileage may vary. But I think if you can afford it, it's great. I think -3/2. All right. Is this a trapezoid again? It kind of is. It's one of those weird trapezoids, I think, where it has like one negative base and one positive base. So, there's another problem. All right, you know what? Let's check. Let's do both of these on the calculator, and then I'll come back and I'll do the other problem kind of on its own. I didn't know that problem was sitting there. So calculator, I was going to say that last one is a trapezoid. It's one of the weird trapezoids that has like a positive and a negative base. And like for whatever reason that works, hopefully you work that out for yourself at some point. So let's see, if f of x is 3x plus 2. So I'm going back to A. I wanted to do the limit. Yeah, the limit as n goes to infinity of the sum. So I'm trying to like type in the overall thing I did. So I goes from 1 to n, and we had f of x sub I was 1 plus 4i over n times 4 over n, and we got 44. Now on the calculator, you of course can just do a definite integral. So we go 1 to 5, f of x dx, 44. For the next one, let's do the integral first. So 0 to 3, x minus 2. I'll just type it in. Get -3/2. So that's what we got when we did it by hand. So I'm feeling like we got them right. I'm going to end this video here. I'll go back to the notes for whatever reason. I feel like this adds like 9 seconds to each video, which the videos are pretty long. Nothing compared to the analysis videos, though. If you watch those, holy cow. So we got it. All right, so maybe I'll just, while I'm here, I'm claiming that this is like one of those weird trapezoid situations. So like if you have your axis, and so when you plug in, so you're going 0 to 3. So we're going to do 1/2 of 3. And then when you plug in 0, you get -2. It's like here. So this is -2. And when you plug in 3, you get 1. So I'm saying that this thing is a trapezoid. It's like very obviously not, but the area you can calculate is 1/2, 3, and then -2 plus 1 is -3/2. So it's kind of a weird thing. You can do that. I do it all the time. It makes me a little uncomfortable to do it, but it works. But anyway, I'm going to stop the video here. I will be back and finish this page. So see you there.